Okay, how's it going? My name is FAMULUS, and my presentation is on amateur nuclear fusion. So let me just start by saying that I am building a nuclear fusion reactor in a lab in Brooklyn, amateur style. So this is an open source project, and it's basically, what we're doing is we're building both a fuser and a polywell, and I'm going to get into what those two things are in a second. But first I want to start with just the basics of fusion and how easy it can be. Okay, so this right here is essentially all that's required for nuclear fusion. You've got two rings. You've got an outer ring that's at ground potential. You've got an inner ring that's at some high negative potential. And then you've got an atmosphere of deuterium at roughly 2 to the negative 2 torr. That's it. Now think of how simple that is for a second. That's like the simplest schematic you've ever seen. It's just two parts of a circuit. And the way it basically works is this potential difference between these two grids, first it ionizes the deuterium in the chamber, and then once the deuterium is ionized, the deuterium nuclei, which have a positive charge, are attracted inward by the negative charge on the inner grid, and they slam head-on right at the center, and sometimes they fuse. And so when they hit head-on and they fuse, you get nuclear fusion. Now this is very easy to do, actually. This has been happening since, we've been doing this since the 60s, basically, is when this was first invented. I'll get into the history in a second. But I just want to meditate on a second on how easy that is. Now, it's when you go to implement this, it's a little more complicated because you've got to build a chamber, and creating this atmosphere of deuterium is not the easiest thing. But that's essentially it. Now, people, when they think of nuclear fusion, typically, they think of a very big machine like a tokamak, really expensive, like billions of dollars, and it's always 30 years in the future. And I'm hoping that this research that I'm working on and this kind of line of fusion research that's going on right now is going to change that and hopefully bring that timeline a little closer to the next 5 years or something like that. So a little history. First of all, this machine was invented by the inventor of the television. Philo Farnsworth invented the television in 1930, and while he was doing research on the television, he discovered that that you could confine a plasma with inertial electrostatics. Excuse me. This power's not on. So Philo Farnsworth invented the television. While he was doing it, he made another discovery, and that basically led to his invention in the 60s of the fuser, which is a functioning nuclear fusion device. And most people don't know this, that the inventor of television also invented a nuclear fusion device. And the reason that we don't know about it is because shortly after he invented it, it was discovered that this device he made, although it does produce fusion, if you try to scale it up to a break-even reactor, it's not going to work. And the reason it's not going to work is because this inner grid here vaporizes. When you get such an intense reaction that you could actually get net energy out of it, that vaporizes. So it's just not going to work. And so it was promptly forgotten about. And also, Farnsworth had some issues with funding, as is always the case. And one company bought the research company, and another company bought it, and it ended up that it just didn't go anywhere. He ran out of funding. The IRS seized his assets, and he died a year later. So that's the story of the origin of the fuser. Now let me show you what a fuser looks like in real life. This is the schematic from the fuser's patent. Okay, this is the fuser that I've built. This is my laboratory in Brooklyn. Okay, so basically a couple elements you got going here. This is the vacuum chamber. The research I'm doing spans both the fuser and the polywell, so it's the vacuum requirements are a little more intense. So this is all conflat. Conflat is the gasket system you see here. So when you see really scientific-looking vacuum research instrument, it looks that way because it's conflat, and it requires a lot of bolts. And inside there is a copper gasket, and it's a one-time use gasket. And when you screw it in, there's a knife edge on the inside of the flange, and it digs into the copper and actually melts the copper, cold melts the copper, and creates one of the best vacuum seals you can get. And so this chamber right here can go really, really, really deep. We can get vacuums really deeper than outer space with this chamber, or at least solar vacuums. right up here, this is the pressure gauge. This lets you know how deep a vacuum you have in the chamber. This is the fuel for the nuclear reaction. This is the deuterium. This is the deuterium system, which feeds the fuel into the chamber for reaction. And then up here, out of the shot, is the high voltage power supply. And it comes in right here with the high voltage feed through. And that basically implements that diagram that I showed you before. Now, this device has not yet achieved fusion. And believe me, not for lack of effort. I was really trying to cross that mark before I got to this conference, but it just didn't happen. But it probably will happen a couple days after this conference. I'm really close. I've been really close about 4 times now. And every time I think I'm about to get it, something breaks or there's another piece to the puzzle. So it's not as easy as it looks, but we're getting there. So a couple other things. This device here is a mass flow controller, and this is a way to computer control the amount of gas that's going into the chamber. So first it's regulated from high pressure down to atmospheric here, and then the mass flow controller allows you to computer control very precisely how much gas you let into the chamber, and this is essential for properly regulating the pressure in the chamber. Almost all of this equipment is the same equipment that's used in semiconductor fabrication. And so as a result, a lot of this stuff is available on eBay for not very much money. So for example, this chamber was $600. This thing I got for under $100. This I bought off of another guy, another fusioneer who was building a fuser and sold it. This vacuum pump, which is this big thing down here, that was pretty expensive. That was like over $1,000 used on eBay. Plus it broke down at one point and required a $3,500 refurb. But this pump is really intense. It's actually 2 pumps. Inside is a rough pump. Let me get a detail on that. Okay, here's a picture of the inside of this pumping. It's called a pumping station. This is the rough pump, and basically that's what most people think of when they think of a vacuum pump. It kind of makes a purring noise, and it'll get you down to about 10 to the negative 3 torr vacuum. And then the real magic is this pump right here. This is a turbomolecular pump, and basically it's basically like a jet engine turbine. And so once the rough pump has gotten the bulk of the air out of it, this thing kicks on, and that will suck the chamber down to really, really deep vacuums, potentially up to 10 to the negative 10 torr. And those are the vacuum levels required for the further research that I'm working towards doing. This stuff is really expensive. Turbomolecular pumps are really delicate and very fragile. I actually totally broke this pump. So we got it. It was working pretty well. Then it broke down. Sent it to the manufacturer, and they fixed it for a lot of money. Sent it back, and then I turned it on without unloosening these screws here that lets the turbo pump kind of vibrate on its own. And the vibrations went into the turbomolecular pump, and I shattered the rotor. And that was like a $5,000 repair. But they didn't charge me for it because they forgot to put a sticker on the outside that said, "Remember to loosen these nuts." So I really lucked out. They basically saved the project. I owe them a debt of gratitude for that. But I mean, what's really fun about this project is every little aspect of it is its own kind of sub-project. You got to learn about vacuum research. You have to learn all about these different pumping technologies. There's a lot of different ways you can pump a chamber down to really deep vacuums, but this is the cleanest and the best for scientific research. Okay, so this is a picture of the actual core of the reactor, and I have the actual device right here. So that's it. And so basically, it's just this inner grid, and this is insulating ceramic, and then this is the flange that connects it to the vacuum chamber. And here's the actual thing you're seeing in the picture there. And this is just made by this is a welding rod, so steel welding rod, and then we form these loops and use brass brazing to braze it all together. This thing is really ugly, and it doesn't work very well. We just replaced it. But I thought I'd bring it along so people could see it. You can pass this around so people can get a feel for what that looks like. That's been in a chamber, has not produced fusion, but has produced a plasma. Okay. So this is what the core looks like disassembled. And so as you can see, it's pretty simple. It's just a wire here. You've got a wire nut, and it kind of all assembles into this system, and then that goes to the high voltage power supply. Okay, this is the outer grid. So when I showed you that first picture, I'll go back to it. This is the outer grid at ground potential. So in real life, it looks like this. And so basically, what this does is it just creates a uniform background, and it has to be the same geometry as the inner grid. And that's the problem with that core that's going around, is it had a different geometry than the outer grid, just because I was lazy when I did it the first time. Of course, it doesn't work, so I had to go and rebuild that. But basically, this just gives you the ground potential, so you get the electrostatic difference. So it's just all about electrostatics. It's very simple. You've got a high negative potential and a ground, and that ionizes the gas and then causes the gas to come into the center. This is the new grid that is replacing the one that went around. This is in the chamber right now. Here's what it looks like assembled. It's a little hard to see, but here we've got the inner grid and the outer grid, and then the larger vacuum assembly. This is the high voltage power supply. These things are badass. Okay, this up here was the first one I got. Goes to negative 10,000 volts at 2 milliamps. This guy goes to negative 30,000 volts at 10 milliamps. Completely computer controlled, current limiting, really awesome. I just got that up and running a couple days ago. That you can buy on eBay for $400. This is what the back looks like. So you can see it can be hooked up to your computer and remote controlled. Now, the way that most of this equipment works, I'm working with a lot of power supplies. And to really do proper scientific research, it all needs to be computer controlled. And so I've been kind of working on that pretty intensely for the last couple months. And what I'm finding is really useful for computer controlling all this hardware are a couple things. One is I've got a National Instruments USB data acquisition interface. And it's sort of like an Arduino almost, but it's like a little heavier duty, higher sampling rates, and it's a slightly different API. But you could use an Arduino for this stuff, and for some of the stuff, I am using that, but for the data acquisition, the actual sampling, I'm using the National Instruments data acquisition device. So once you've got that in place, that's really useful, but it doesn't necessarily allow you to control this equipment. And the reason is because the data acquisition device only outputs 0 to 5 volts as its control signal, and this takes 0 to 10 volts. And so what I'm ended up doing to solve that problem for a lot of the stuff is using a microchip called a digital potentiometer. So you guys all know what a regular potentiometer is. It's just a variable resistor that you turn. So this is like a chip that you send. Basically, it's ones and zeros up and down to step up the resistor ladder or step down the resistor ladder. And so then you can have a really simple binary digital interface to send these pulses to it and control the resistance, which then controls the voltage or the current on this thing. Additionally, on these slots right here, 4 and 8, you can monitor the voltage and current coming from the power supply, which is very important because a lot of this research involves how efficiently you're making the fusion happen. So like you have to know how much current you're using, how high the voltage is. Because one of the things that happens once you've got the plasma running, it actually produces a current. And so that lowers the voltage, of course, and balancing all of those things to find the sweet spot of the reactor is sort of what I'm in the process of discovering right now. Now, why is this interesting if it was proved that this thing isn't going to work, basically, and it's been forgotten? It's a kind of a forgotten technology because this inner grid is going to burn up, that thing you're passing around. If you made it too big, the fusion would happen too much and it would burn this inner grid up. Well, why it's interesting is because in 2008, this guy named Dr. Boussard released a video called "Should Google Go Nuclear?" And it basically documents the research that he's been doing since the 80s. And he has invented a modification of the fuser, which has the potential to scale up to a true working nuclear reactor. And that's what really got me excited about it, because I saw a real opportunity here. It's like this is amazing. This is possibly the cheapest and easiest potential way you could get to something like a working nuclear reactor, and it's just right here. It's been released. The information's out in the open now. And like a couple of months after he gave this presentation, he passed on from cancer, and so now nobody's leading this charge towards this new kind of fusion device. But enough information has been released to the public that an open source, sort of community-oriented effort could produce this device. I really believe this. I really believe that this could lead to a device that will change the world as we know it. Let me show you some pictures from that. So these are some images from Dr. Boussard's work. The company that he runs is called Energy Matter Conversion Corporation. It's out in Santa Fe. And the device is called the Boussard reactor generically. Their trade name is the Polywell. And most people know it as the Polywell. So this is what a Polywell looks like. Now, it does the same thing as the fuser essentially, but it does it a little bit differently. It's more complicated, but it avoids some of the problems that you are going to run into with the fuser. So what we have here, a grid, much like the inner grid of the fuser, but now we've got electromagnetic coils inside. Okay, and then this is as it's being built. When it's done, lids go on top of each of these coils, and it gets welded together and put into a vacuum chamber. Now, unlike the fuser, where the grid is negative, this skin is raised to a very high positive potential. And the idea being that you're going to shoot electrons from an electron gun coming in these cusps, and the high positive potential first attracts electrons into the center, and then those electrons form a virtual cathode, which then attracts the deuterium or whatever your fuel is for fusion. Now, the magnets do two things. The magnets, first, what they do is they further constrain the electrons because a moving charged particle in a magnetic field is constrained. And so basically they pinch the electron plasma into a tight ball. And most importantly, they insulate the metal. Because the thing is, if you've got a high positive potential here, all those electrons you're injecting, if there's no magnetic field, they're just going to go right into the high positive potential, and you lose all your power to run the thing. That's the key thing he discovered, is you have to be really careful about not letting electrons get into the metal. And so everything has to be very carefully magnetically insulated. So even these joints that connect the things have a couple wires of electromagnet running through them so that they're insulated. And there's still a lot of research to be done on this particular topic. And my understanding of the Polywell is still something that's kind of like I'm learning every day. The fuser, I feel like I understand pretty well already, but this is more complicated. Okay, so here's what it looks like running in the full machine. So this is the device in situation. This is the vacuum chamber all around the outside. This is the core. It's called the mag grid, which is a contraction of magnetic grid. And here you've got a Faraday cage all around the outside. That's the same thing as the outer grid in the fuser. That's a ground potential Faraday cage. And then here you can see the electron injectors. And then also one of these is a deuterium injector. So the way the operation would work is first you fire up the high positive. First you clear out the chamber so you get a vacuum. Bring this to a high positive potential. Turn on the magnets. Inject electrons. Well, first you inject the electrons, then you turn on the magnets. See, I don't really know how that actually works because I haven't done it yet. So until I actually built this thing and have operated it, I'm just guessing. There's some documentation out there. It's not incredible, but it's a good start. But basically, you create an electron cloud in the middle, and that's the virtual cathode that the fuel is going to be attracted to. You release the fuel into it. It either ionizes because of the differential, or you shoot some microwave to ionize it, and then you get fusion. And supposedly, according to Boussard's research and his assertions, this device, if built large enough, could be the first break-even fusion reactor in the world. And his estimates for large enough are 3 meters across. So 3 meters from here. So that's about, that would fit. It wouldn't fit in the room because if the room was a little taller, we could fit it, up here. But that's just the inner part. You still have to have the vacuum chamber and all the other stuff. Now, let's say that all this works and you produce fusion at a high enough rate that you could actually have a fusion reactor. How do you get the energy out? Because right now, you've got a reaction here and bam, these things are flying out of there at high speed. And the byproduct of the deuterium reaction is fast neutrons, helium-3, tritium, and some X-rays, more or less. Those things are flying out of there at high speed. So if you were using a deuterium fuel, you could put it through a traditional thermal cycle like you would have at a coal plant or like a traditional nuclear reactor. But there's an even better fuel mixture that avoids a lot of those issues with radioactivity that ultimately this is designed to work with. And that's what makes it really exciting. I'll get to that in a little bit. So basically, this is the work that Dr. Boussard done. There's a great video online of a presentation he gave right before he died called "Should Google Go Nuclear?" And it's really worth watching if you have any interest in this, because he explains his work better than I ever could. Okay, so some other pictures. So basically, the idea I had was, ultimately I want to be building a Bussard reactor and do research on that. But the stepping stone to doing that is the fuser, because it's the lineage of the Bussard reactor, and it has so much in common. The vacuum chamber is the same, high voltage is the same, a lot of the electrostatics, the deuterium control is the same. So by building a fuser, you get like 90% of the way there, and then there's just a little extra bit to do the actual Bussard reactor bit. Okay, just a couple kind of sort of interesting things about working with high voltage. High voltage is very dangerous. Definitely could get killed with 30,000 volts pretty quick, and there's no second chance with that. So you got to really know what you're doing. I don't necessarily know what I'm doing, but so far I haven't killed myself. This is the cable that comes out of the back of the machine. Interesting. It's sort of like a beefed up coaxial cable. The high voltage comes in right here, and then starting here, you've got like an outer Faraday cage, like you would have with a coaxial cable that's grounded. Now, when it's used in like audio video, a coax cable is useful because it shields the signal that's inside. In this case, it does a similar thing, but it's shielding you from the potential escape of the high voltage. So if there's an over voltage for this insulation, the Faraday cage around the cable will catch it, and you won't get electrocuted. Very important. You have to use these proper cables. And then on the other side, where it goes into the reactor, you have to have at the very least, a glass tube insulating the interface so that you can't get your hands in there. And you really don't want to be anywhere near this thing when it's running. That's the greatest danger of this research, is the high voltage electricity, which means it's dangerous for the researchers, not necessarily for anybody outside of the lab. But it's really dangerous. Okay, so basically, let me show you some plasmas that we've done. Oh, one other thing that's really important, grounding. It's got to be really grounded well. You can see here we've got some serious grounding. We've got ground going up to the water pipe up in the ceiling. And we've got several different outlets that are all tied together into a star ground, different contact points all over the reactor, the pump, the high voltage system, the rack unit. All that stuff is really grounded really well. And that's what keeps you safe, because if there is something, an arc that jumps into the system, the ground will take it away instead of letting it go into your body. Question? Well, I mean, I can't really give you an answer on that because I haven't gotten it functioning yet, but I don't expect a lot. It's the amount of energy that you get out of the fusion reaction is directly proportional to the voltage level that's going into it and how stiff the voltage is under the plasma current. The power supply that I have right now is probably on the bottom end of even getting fusion, and I haven't even been able to get it yet. So first we got to get it, and then there's a whole topic of ionizing radiation safety. I haven't quite gotten there yet, but that also is important. So here's what it looks like when you have a plasma. This is really exciting. This was a couple days ago, or not. This is a couple month ago about that we got our first plasma. And so basically, this is a plasma with air. So first you test it out instead of with deuterium. You just put a small amount of air into the system. So this works by you drop the vacuum down really deep, and then using that mass flow controller, you release a little bit of air into the system, and you get a stable, low-pressure atmosphere inside of there. And then when you turn the high voltage on, you get this. And so basically what's happening is the high voltage is ionizing the gas, and then the ionized gas is rushing into the center. And so you can see it forms that little bulb in the center, and that sort of would be like where you would have your nuclear reaction if this were deuterium. This is the deuterium. This is the fuel for the reaction. Amazingly, it's pretty easy to get your hands on this stuff. It's not a controlled nuclear substance. It's not radioactive. It's slightly toxic. You don't want to be breathing it. In case you don't know, what deuterium is an isotope of hydrogen. So it's hydrogen that has an extra neutron. And this makes it a perfect candidate for fusion because it's the extra neutron makes it more susceptible to the fusion process. So deuterium reaction is one of the easiest nuclear fusion reactions you can do. The only one easier is deuterium-tritium, but that's difficult because tritium you can't really get your hands on very easily, and nor would you want to. So this I got from Matheson Trigas. They're up in, I think they're in somewhere in Massachusetts, I think. And yeah, I mean, it's this bottle was about, I think, like $300, for this funnel. It's not a whole lot of deuterium, and you have to meter it very carefully or you'll waste it right away. Anytime we're running this thing, we've got an exhaust vent in the laboratory that evacuates any spent deuterium or any byproducts that you might get. But I was really surprised how easy this was to get. They do make you jump through some formalities. I had to have a proper email address that matched my company name, and I had to be incorporated and some stuff like that, but pretty basic stuff for people that do research. Any questions? Okay. Yeah, go ahead. Well, what we're seeking to do with the plasma is to create the fusion, and that will produce the energy that eventually we'll capture. The plasma itself isn't really interesting, but what it can do is interesting. But it's the first step towards an actual fusion reaction. So some other, this is how you know you've produced fusion. This is a bubble detector, and it's boron trifluoride, I think is the chemical in there. And basically what this does is if you have fusion, you'll get a bubble in this detector. And the only way you're going to get a bubble in this detector is if you have a fast neutron from a fusion reaction. So it's a very easy, very reliable way to know if you've actually done it. And then furthermore, you can quantify how much fusion you have by how many bubbles you see in this reactor. So that's how I know I haven't done it yet. Here it is in situation. Now this is kind of interesting. See how that detector is right over a piece of metal? Like, how does that work? Well, that's because the thing that's coming out of those are fast neutrons, and they will go through anything. So a slab of stainless steel will not stop a fast neutron. So you can put it right over the metal. Ultimately, going along with that, it'll go right through your body. So neutron radiation is very ionizing and very dangerous, and you don't want to be anywhere near this thing when it's running. Boron, it's very dangerous. The manufacturer claims it comes in a shatterproof plastic container. That's shatterproof. Really, I haven't tested that, but. So a couple usage tips on these bubble detectors. You have to unscrew the back of them to activate them, and they have to be within a certain temperature range. And there's a little indicator on, you can see it up here. There's a little kind of LCD temperature indicator, so you know you're within range. That was very important. I realized one day when I was doing my second attempt that I wasn't in range. The lab was a little bit colder than was supported by the detector, so I had to put it in my pocket for a second to warm it up. This is our first fusion attempt. This is a deuterium plasma. It looks blue where the air looked purple, but I don't think we can really trust the colors I'm getting from my camera because I've seen the same plasma look a couple different colors. This is at like a pretty high pressure, full voltage, and this is another one with a slightly lower pressure. Space. I can't say that I really know exactly. I'm really excited for when we can actually produce our first data results on this. This, let me show you. This is a video. This is a video of the plasma in action. Okay, so see all those sparks kind of happening on the grid? That's because my grid sucks. You'll see it. It's really ugly when you get it. It was like my first brazing I've ever done. And so all those little imperfections basically create like a sort of they just make it spark and really ugly. And you can see it's not very strong right there. So I'm hoping that the new grid, when we test it out, gives us a kind of a stronger, more focused fusion plasma. But that's what it looks like running. This is the data acquisition device that I'm using to control and acquire data about the reactor. Okay, so a couple things. How do you meter really high voltage? Well, the easiest way is off the back of the high voltage unit. This new one I have has an output for that, so that's great. But outside of that, you can still actually get a contact in there and take a measurement of that high voltage. And the way you do it is with a voltage divider. Anybody that's an electrical engineer will know what that is. And it's one of the simplest circuits you can build, and it basically takes an input voltage and divides it by some ratio. So I bought a professional high voltage divider that's designed for these kind of voltage levels to safely measure and insulate you from them. And so what it does is divides the voltage by 1,000. So if you're doing 30,000 volts, your meter will show 30 and keep you out of the loop. So this is basically, it's pretty simple. Basically, you have multiple inputs. It's like a sampler, like on audio sampling for digital to analog to digital. And you've got several inputs, and basically it'll measure any voltage from 0 to 10. And it can output voltages from 0 to 5, has digital ins and outs as well. Pretty easy to use, pretty cheap. You can get that on eBay. Yeah, question? This is some hardware hacking that I got to do. There's a lot of hardware hacking in this project. This is a magnetometer that I bought on eBay. And then after I got it, it worked great. But after I got it, I realized there was no output so that you could connect it to the rest of the system. So I called the manufacturer, and I'm like, is there any way you can, like, tap this thing and put that in? He's like, yeah, there is, in fact. And so they sent me some diagrams, and basically we got to open this thing up and put a little lead in, and I kind of glued in this interface right here, and it works. And so now I've got a really good digital magnetometer for this, and this is to measure the magnets in what will be the Bussard reactor. These are IGBTs, and basically what these do, these are like really high power transistors. And so these can switch, as you can see here, 200 amps at 600 volts. Crazy. That's a lot. I mean, if you really think about 200 amps being switched by a transistor, it's ridiculous. So these things the Bussard team bought, it's amazing. There's a document online that details all of the different things that the Bussard team bought for their research. It's really helpful, and they bought like hundreds of these things. So for all the switching they need to do to turn all that power on, turn it off really quickly, they use these things. And these things can even be like pulse width modulated, so you can really quickly turn on and off extremely high currents and voltages. Real cool stuff. These also bought on eBay for like $15 a piece. Okay, so this is my first attempt at an actual Bussard reactor, and this is the actual part right here. And I can pass this around. There are two pieces. There's a lid and a base. Please get these back to me. They're very important. This is really cool, the story of how this is even made. Let me show you a little program that I wrote. Oh, you guys didn't get a chance to see that? Here you go. So basically, this is an open source CAD program called BRL CAD. This is originally a military software, and they open sourced it at some point. It's a solid modeling geometry program, and so basically you say, give me a torus, or give me a cylinder, or give me a cube, and then you can do algebra on these different shapes. So you can say, give me a torus and subtract a cube, or give me a sphere and subtract another sphere. Really versatile, and it was absolutely ideal for this type of stuff I was doing, since it was all very simple geometric primitives. Now, what I did to actually create this shape is, it's a Ruby program. I'm a Ruby programmer, so it's the language I went to naturally. So it's a Ruby program that's actually talking to the BRL CAD program to create these shapes. And the advantage of that is I can have a really powerful abstract Ruby program that takes into account a lot of the mathematics behind the shape and the ideal shape that you want, and then outputs to this CAD program. What's even more amazing is I can go directly from this CAD program to that metal shape that's going around in one step. There's this company called ProMetal out in Pennsylvania, and you can send them a CAD file, well, really an STL file, which is a type of CAD file. So you guys are familiar with MakerBot? So that's the format that MakerBot uses. So basically, it's just the same process you would do to print something on a MakerBot. You can print something in stainless steel. Amazing stuff. Now, unfortunately, that part that's going around can't actually be used. And the reason is because that metal is magnetic. And ultimately, the metal we need to use in this thing can't be magnetic. It can't have a magnet stick to it because it has magnetic fields coming out of it. But still, just as a demonstration and a display, it's really useful. And I found another company, a Swedish company called Arcam. And these guys have a really amazing process. They can make similar process. You send them an STL file, and they can make a fully solid titanium part, completely melted. You can make a jet engine turbine out of their process. Amazing. So that's what we're ultimately going to build this thing out of. Now, that process is more expensive. To produce a part like that would be like $3 grand. So we've got to really make sure we got it right and take your one shot. I think I'm going to do a version with this metal, and with the understanding that it won't work, but it'll help us solve some of the related problems. Like, for example, the coil, there's a coil inside of that. And in our case, it's going to be a superconducting coil. That coil is going to be at ground potential, and the chassis around it is going to be at like positive 20 to 50,000 volts. So that's really difficult. You have to insulate, these two things that are really close together. Now, like varnish that you would use for magnets, that will give you enough insulation to do that. But, how do you apply it? How do you get it consistent enough? Because I'm sure if there's any little spot that doesn't have enough coverage, that's where you're going to have a short out and you'll blow the whole device. I'm sorry? And the magic smoke comes out, yes. So I mean, basically, okay, so the real ambition of this project, and the reason that the research I'm doing is worth doing, is that I'm trying to do something no one has ever done before, even the team that has invented this technology, and that is to build a superconducting version of this Bussard reactor. Just a small one, not a prototype reactor, not a break-even reactor, or anything as ambitious as that. And that's very important. Everybody understands that ultimately this thing needs to be superconducting for a couple reasons. One is because a superconducting magnet doesn't require additional electricity to keep it going. So it's to get the energy efficiency, you would need to have a break-even reactor. It has to be superconducting. Furthermore, a superconducting reactor has the potential to allow you to make a smaller version that can reach break-even, because superconducting magnets can be much smaller than their copper coil counterparts. So there's this really tantalizing possibility that the fruits of this research could be a scaled-down reactor, and that's really exciting, because this thing is cheap even at the full size, and by cheap I mean like $20 to $100 million, which is cheap for nuclear reaction research. But to have something that can go even smaller than that is really, really exciting. Now, there's been some advances recently in the superconducting field with high-temperature superconductors finally coming on the market. What I'm using is this stuff called yttrium barium copper oxide, otherwise known as YBCO. And this stuff will go critical in liquid nitrogen. Now, that's great, because before you had to have liquid helium. And to use liquid helium, you also have to have liquid nitrogen in this very complex two-stage cryogenic system, and it's just really tough to work with. Liquid nitrogen is very easy to work with. I've done it already. We've already done a superconducting magnet test somewhat successfully, and I'll show you some pictures of that. So that's the superconducting magnet coiled around inside there, that coil there. It's a really thin tape. It's amazing that this stuff, that little tape, it's like paper thin. When it's superconducting, it can carry 80 amps, which is amazing. Superconducting levitation right there. So this is the stuff that I got. I got this stuff from Germany. Actually, it's an American company that got sent to Germany, and then I bought it from the German company. They sent it back to me. A little ridiculous, but it's kind of hard to get your hands on. So this is the superconducting magnet in the original spool that I got it in. This is liquid nitrogen kind of bathed all around there, and this is just a regular magnet. The magnet's white because of the liquid nitrogen has made it frosty. But there you can clearly see the Meissner effect in action. That thing is floating there. It just sits there and spins around. It was really awesome. And this shot was hard to get, but I finally got an actual shot of the levitation. I'm really happy with that. This is our superconducting coil test bobbin. So this is basically, I designed this and it's cut out of laser. It's laser cut acrylic, basically, simple construction technique. The coil is wound up here. Here is the high current connects, and this little thing in here is my first prototype persistent switch. And what a persistent switch does, okay, so an ideal superconducting magnet is an infinite loop. It's a coil, and the two ends are mated together. And just imagine somehow you got a current in there. It'll just go forever. Amazing. As long as it stays cold, the thing will just run forever, and you basically have a permanent magnet. But how do you charge it up? Well, the way you charge it up is this little section here. Okay, see this ropey-looking stuff? That's nickel chromium heating wire, actually taken directly from my rep wrap. So the rep wrap for its heater barrel has a nichrome heater, right? To melt the plastic. Same thing here. Same circuit even. This is where I'm using the Arduino. Now, how this works is when superconducting material is cold, sub its critical temperature, it conducts with 0 electrical resistance. But when you warm it up, it conducts at the resistance of copper, which is much higher than 0. So basically, by heating this little section, you create a resistor temporarily. And with that resistor there, you're able to apply a current between these two junctions, and the resistor forces it to go through the rest of the cable. So you slowly turn up the current, and stronger and stronger magnetic field generates in that loop here until you've got the full magnetic field. And then what you do, you turn the electricity off in the heater, and that cools down to critical, and then you remove the electricity from the terminals, and it just goes forever in a loop. Haven't gotten that far yet. We've put a current through it in liquid nitrogen, and it works, but I haven't gotten the persistent switch working. And to do that, I have to completely computer control this, because it's all got to be precisely switched on and off, and probably will take some experimenting about the timing of the different things. And that'll be really interesting, because I don't know how this works. I've never done this. There's not a lot of documentation on it. Yeah? We could definitely do that. This is the way it's traditionally done. Like from the research I've done, typically they recommend using a persistent switch. You can probably charge with an inductance, but I don't have the apparatus for that, and it's just not the path I've gone. Okay, so, and here's a picture of the cryostat. So this is just a Dewar, eBay, $200. You can get it filled with liquid nitrogen for like $60 from a welding supply. Really cool. That's fun just to play with. Some safety things with liquid nitrogen. It'll burn your hand if you get anywhere near it. It can really badly burn you by freezing. And if you spill the container in a closed space, you can suffocate because the nitrogen will block out all the air. So it's a little bit dangerous. You have to be careful with the liquid nitrogen. Very good for that. Advanced culinary arts, awesome. Okay, so this is a close-up of the mass flow controller, which I just installed like a couple weeks ago. Basically just a op-amp power supply, plus 15, negative 15 volts on here, simple. And then the power supply goes in there, and then this goes to the digital acquisition device for computer control. And you set a voltage between 0 volts and 5 volts, and that controls how much gas is going into the chamber. That works really well. Before that, I had a little needle valve that I had to like crawl up into the reactor while it was running, and it was not good. So I'm really happy to have this online. And as you can see, now that I've got the mass flow controller up and running, I can hit precise chamber pressure. So this is the vacuum gauge on the main chamber. This is called an ion gauge, and this gauge can read down to very deep vacuums. It tops out at like 5 to the negative 2 torr, so you can't get the kind of the atmospheric to mild vacuum readings on this, but I haven't needed it yet. This is just some fun stuff. These are some power supplies that came out of an old Cray supercomputer. These things are, I think they're 300 amps each, or are they 600 amps? Let's see here. Yeah, they're 400 amps each. So I'm hoping to use these when we get to the polywell to control the electron emitters. I don't know if it'll work or not, but they're really cool, and they came from England. So throw those in there. Some mistakes I've made along the way. This is the first vacuum chamber I bought. Didn't work. Fortunately, I sold it for exactly what I paid for it on eBay a couple days ago. So got out of that one. This is so large that you could fit a person inside. And this was originally used for making compact discs in the research phase. So this would put the silver on the compact disc and have this whole mechanism inside, like a carousel. Really wild stuff. Didn't work, but pretty cool. I wanted to show that. Okay, so now a little bit about fuels. So what's really exciting about this reactor is the mix of fuels that it can run. Now, the tokamak, which is the traditional reactor, that all it could ever run or hope to run is either a deuterium-deuterium reaction or a deuterium-tritium reaction. And what's really exciting about the polywell is instead of where the tokamak tries to heat the whole plasma uniformly, the fuser and the polywell focus, and it's only hot right at the center. The rest of it's basically very cool gas. And furthermore, all that heat is focused in one little place, so it's a much more efficient heating of the gas. So what that means is it can burn reactions that are higher up the scale in terms of like energy needed to create the reaction. Now, almost all the research that's done in fusion is deuterium, deuterium, or deuterium-tritium, because it's the easiest to instigate. But this one down here is the real promise. And this is the promise of a truly environmentally friendly, non-radiation producing nuclear reactor, if you can believe it. Now, the device that I'm working on, as soon as you turn it off, it's no longer radioactive. It only is radioactive for the duration of its operation. Furthermore, it requires a very delicate set of parameters for that to even happen. So it's much safer right from the bat than anything that you could ever get with fission. There's no chance of a runaway reaction or anything like that. It's very contained. And when you turn it off, it's non-radiation producing. With one caveat, when you're producing a lot of neutrons, if you're producing a lot of neutrons, neutrons that fly out of this thing can embrittle and imbue radiation in the surroundings. So basically what happens is a neutron can hit, a steel nucleus and make it unstable and make it radioactive, basically. So it's not perfect, but it still is a lot better than fission. Now this reaction down here, this is called the PB11, or the proton-boron 11 reaction. This is really exciting because it produces no radiation. It's called aneutronic radiation. I'm sorry, aneutronic fusion. And so this is the real promise. Now, it requires a much higher initiation than the deuterium reaction, but the product of it is helium atoms, ions. Helium ions come shooting out of this thing. And so they're not neutrons, so they're not radioactive. And furthermore, what's most exciting about this is because helium ions are charged particles, you can capture the energy with a direct-to-DC electric capture mechanism. And there's a paper out there called the Venetian blind mechanism that's been proposed to actually do this. Now, I'm nowhere near any of this stuff. This is research for way in the future, but it kind of gives you a taste of where this technology could lead. So imagine this device in the Bussard reactor. You're getting this fusion with proton, which is hydrogen, and boron. They come together, they fuse, and they split off as 3 helium ions. These helium ions go out of the reactor, and they are captured by these Venetian blinds that convert the electricity with something like 80% efficiency, something way above what you get with a thermal cycle, to electricity, DC electric. It would just be this giant plus and minus terminal on the outside of this thing, just like pure raw DC electric. Really cool. So this is exciting because this promises to really be, it's the future. The PB11 reaction gives you a high efficiency conversion to electric and almost no tangential radiation. There's a small, tiny subreaction that happens, like 0.1% of the reaction, that does produce some neutrons, but relative to the energy that's coming out of the thing, it's minuscule, and it's probably manageable in terms of the ultimate technology. And this is a 60-watt laser that I bought and fired up just to burn stuff. That was really cool. That's what you can do. You got a lab, you got all this equipment laying around. It's like, hey, let's make some crazy stuff. All right. So basically, that's what we're trying to build. Has everybody got a chance to see the inside? Has that gone around? Okay, have you guys seen it on this side? Okay, well, I think I'm going to open the floor up to questions. Right, well, there's 2 ways to capture it. If you're running a deuterium fuel, it's a thermal cycle like you would have with a coal plant. So the neutrons would heat up water, that would produce steam, and then you have turbines. And if you're running the PB11 reaction, it's a direct-to-DC capture with the Venetian blind system. I can't really tell you too much about that because I don't necessarily understand it that well. Because it's, first you got to create the fusion, then you worry about how you're going to capture it. So that's research for a little further down the road, but there is already a blueprint for how we would do that.
So when you get this thing working, what's the potential of making Brooklyn into a Frank?
I get that all the time.
Really, that's from a non-physicist point of view.
Right.
You're freaking me out.
Okay, fair enough. That's a good question. I get that all the time. Realistically, this thing I'm making probably isn't going to impress much. If we get a couple bubbles in a detector, that's success. The high voltage is the real risk. And beyond that, if you actually do get it to produce fusion, you don't want to be near it because that thing is basically X-rays and neutrons are going to be coming out of it. So, for people in the lab in the immediate vicinity, and I'm talking like 50 feet away, that's about as far as away as you need to get to where they would drop off to regular, like background radiation. As I get closer to actually fusing the atom and begin to cross that threshold, I'm going to do another round of safety reviews and best practices. I just haven't gotten there yet, but there's really no chance that I'm going to be blowing anything up. I mean, conceivably you could, the fuel is basically hydrogen, so that's explosive. But when it's going into the chamber, it's only hydrogen. There's no oxidizer, so it can't really ignite. I'm not really sure. Yeah, there's nothing. It's dangerous for me, but it's not really dangerous for anybody outside of the lab. Now, as these things get bigger, it can't happen there. Like once it goes beyond a certain stage, I need to take this operation to New Mexico and get a facility in the desert. Well, I don't think he died of cancer because he was doing fusion research. He smoked cigarettes too. So, and one thing I would like to say too is that I'm not the only guy doing this. There's a long history of amateurs building fusers. If I fuse the atom with the fuser that I'm building now, I'll be the 26th person to ever do this. So there's a lot of guys. A high school student has created fusion. The University of Wisconsin-Madison has a program that's researching this, and so a lot of people have done this without blowing themselves up or their neighborhood. And I think it's very important too because it's like for me to continue to be able to do this, it needs to be understood that it's not going to lead to a serious problem because I want to continue to do this research. Well, my main goal is to build the world's first superconducting Bussard reactor. I think that's really important because it tells a really interesting story. And so where I want to see this go is I want the story to kind of get out there, that this is possible and that it's happening. And that's hopefully what will lead to whatever money I need to really take it to the next step. Well, okay, so to be clear, no one has ever had a break-even fusion reaction. We've never produced net energy from fusion. That's the holy grail of fusion research. So I'm not going to do that anytime soon, and neither is anybody else, most likely. Now, ITER says that they are getting close. We'll see. Now, in terms of cost, fusion per dollar, nothing is going to beat this technology. It's the cheapest. Absolutely, absolutely, but there's a long road. Yeah, absolutely. That is the ultimate goal, but there's a long road between what I'm doing now and that ultimate goal. And it takes a lot more money. As I said, it's got to be 3 meters across, so it's going to be millions and millions of dollars to fabricate a machine like that. It's going to have to be out there, insured, government sanctioned, all that. Yes?
How do you compare the cost of tritium
I can't answer that question. I don't know. This would probably not run on tritium. Tritium would potentially be a byproduct of the deuterium reaction. Okay, so the question is, how much of a problem is there with the equipment becoming radioactive from the fast neutrons? That is a concern. I don't think I'm going to be doing that much actual fusion in the research. It's sort of all about leading up to it and then a really brief test. I don't think for the prototype stuff that I'm doing, it's going to be much of a problem. Now, for the real reactor, that's a significant problem if you're doing the deuterium fuel, but the real advantage of the proton-boron reaction is that you don't get that. You don't get the massive fast neutrons and the embrittlement that comes with it. Well, basically, that thing that's going around, the magrid, That'll be welded shut, and there will be a feed-through that passes liquid nitrogen right into the center of that. I'm sorry, I'm not repeating the questions. I should be doing that. Yes?
Are you funding yourself?
Yes, the question is, am I funding myself? I'm self-funded for now. Before this, I was a Ruby on Rails consultant, and I've saved up some money from that. And so the budget for this project is about 20 grand, and I'm working through that now. And I hope to get to the superconducting Bussard reactor before I run out of money. Has the power company noticed my experimentation? No, they have not, because I don't use much current, really. The high voltage power supply to create the electrostatic difference doesn't pull a lot of power. It's just a high potential. So far, not really much at all. Right now, we're using an earth ground for the outer grid. The question is, are we using an earth ground for the outer grid or a floating ground? Now, right now, we're using an earth ground, but ultimately, I would like to switch to a floating ground, the reason being so that you can monitor how much current is going through the ground, and you know like what losses you have to ground. Any other questions? Mm-hmm. That's a good question, and it's not one that. The question is, what are the laws for generating tritium, and which is a controlled substance, and that the laws around that. I got to be honest with you. I wish I knew more about that. I'm trying to find a lawyer who specializes in nuclear regulatory law because I don't think I've broken the law yet, but I'm not entirely sure. I'd really like to know that. We are not capturing tritium, which I think is the real problem. But I would like to know that, and I would like to know it before I actually do that. So if any of you knows a lawyer, probably you don't. But, it's really hard to find. It's like I don't even know where these guys are. I even called, the research. I talked to a guy at Los Alamos. I'm like, what do you guys do for your legal? And he's like, we have a department. He's like, I don't know what. Somebody else takes care of that. So I didn't get anywhere with that. Questions? Yeah, I mean, we're talking like a whiff at best. If I was lucky, it would be a whiff. I'm sorry? Dr. Bussard was funded by first the Department of Defense and then the U.S. Navy. And although he's passed on, his team is continuing this research, and they just got $10 million to do the next round of prototypes. And they're out in Santa Fe, New Mexico. I don't think he was connected with Los Alamos. Any other questions? Yeah. It's mostly just me, but it's an open source project, and I've got a lot of people that comment really constructive comments on the blog, and I've got various friends and people helping me. So I'm the motivating force, but it's a team effort. Cool. That's it. All right. Thanks, guys.